All right, what is the energy in kilojoules per mole of photons corresponding to the shortest wavelength line in the series of hydrogen spectrum when m equals 1 and n is greater than 1? So what we're talking about is we're talking about an energy wavelength being emitted as an electron falls from one position to another. Our electrons in an energy level where n is greater than 1, and it's falling to m equals 1. Our electron falls, and as it falls, it emits a wavelength. That's what we're trying to figure out, what that wavelength is going to be. Now, the question is twofold. First, they want to know what the shortest possible wavelength that can be emitted is. Well, whenever you see the shortest or longest in a question, you know you're going to extremes, right? You're going to be like Billy Joel and go to extremes. Well, the extreme is going to be generated when n is equal to infinity and m is equal to 1. Because that's going to be your largest difference in energy. Is if you're infinitely far away from the first, or you're going to have your smallest distance and difference in energy, where n is equal to 2 and m is equal to 1. And that's going to be your smallest difference in energy possible if we're falling to the first energy level each time. Smallest difference in energy. So the question we have to ask ourselves now is, which of these two extreme possibilities is going to generate the shortest wavelength? What is the relationship between wavelength and energy? Well, they're inversely related. The higher the energy difference, or the greater the energy, the smaller the wavelength. So since we're wanting the shortest wavelength, we're wanting the largest energy difference. And that's going to be when n is equal to infinity. So far, so good? Now that we know that we're looking for n equals infinity to m equals 1, we just have to know what formula to use. And we're just going to use the same boring Reisenberg formula that I gave you in class. And this is one of the advantages of listening to my lectures as opposed to reading your book, because your book's version of Reisenberg is terrible. They deal with that inverse wavelength, whereas everybody else from the face of the planet gives you energy. That difference in energy is equal to the opposite of the Reisenberg constant times the quantity 1 over n squared final minus 1 over n squared initial. Okay. Now we just need to plug in our values. Again, this is where having me for the lecture or listening to my lectures actually helps, and taking notes on them. I give you in your notes a value for the Reisenberg constant in this form. Just like I gave you this formula, I give you a value for the Reisenberg constant for a hydrogen-like atom for this form of the formula. And it is 2.18 times 10 to the negative 18 joules So we have our Reisenberg constant. We know that it's falling to n equals 1 here, and it's falling from an initial state that is infinitely far away from our nucleus. So now it's just a matter of straightforward algebra and plug and chug, with one twist that causes some people a little bit of difficulty if you haven't had calculus. So we've got the difference in energy is equal to the opposite of 2.18 times 10 to the negative 18th joules times 1 squared, 1 over 1 squared, minus 1 over infinity squared. Well, a little bit of quick math here. Infinity squared is infinity. 1 over infinity approaches 0, right? As the bottom number of a fraction gets larger, the fraction gets smaller. As numbers get infinitely large down there on the bottom of your fraction, you get closer and closer to 0. So that is said to be approaching 0, which means we can treat it as such for our purposes. So that gives you a difference in energy equal to negative 2.18 times 10 to the negative 18th joules times 1 over 1 squared, which is 1, which means that your difference in energy is equal to 2.18 times 10 to the negative 18th joules. So now it's just a matter of converting to wavelength, which you can do at this point like you're standing on your head. You've done it so many times. Energy equals Planck's constant times frequency. Oh, whoops, where am I going with this, by the way? Do I need to, did that ask for the wavelength? What is this? What is the energy? Yeah, they're asking for energy in this problem, so we don't need to go to wavelength. I'm glad I decided to step back and read the question again. Okay. The question is asking for energy, but notice the units here. It's wanting kilojoules per mole of photons. And that's the other area that causes people a little bit of problems with this, that kilojoules per mole of photons. This Reisenberg formula and this energy value that we have right here was caused by the fall of 1 electron, meaning it corresponds to 1 photon. So we're going to have to do a little bit of unit conversion magic here, but that's okay. You guys are old pros at unit conversions. Now that's per 1 photon. We're wanting per mole, right, of photons. So we know that there are 6.022 times 10 to the 23rd photons in 1 mole. And we know that, so now we've gone from joules per 1 photon to joules per mole. because we've crossed out photons, right? Now we want kilojoules. So we're going to place our joules where they cancel out. We want kilojoules. We know that 1 kilojoule is 10 to the negative third joules. I mean, sorry, it's 10 to the positive third joules. So now I just multiply everything on top, divide through by everything on the bottom. Now we actually have to pick up our calculators for the first time. That was a really awkward punching in here. 2.18. Days like this, I miss my office. Ah. And that gives us 1.313 times 10 to the third kilojoules per mole.